All right, we have a flat plate here with uniform density, and we would like to find the centroid. So the top part of this region is defined by f of x, and we're going from x equals a to x equals b. And we're going to break this down into rectangles, like we like to do in calculus. And we're going to define the height of each one of these rectangles is going to be f of x at the midpoint of each interval. Okay, and so if we are looking at one of the individual rectangles that we have here, okay, I'm going to say that this is the ith rectangle, and we're going to say that x bar sub I is the midpoint of that ith rectangle. Now, to find the centroid of that rectangle, the center of mass for this, it's going to be somewhere along that line right there. And in fact, we know that the height of the rectangle we are calling f of this special midpoint here. And so the centroid for the ith rectangle which we're going to just call c sub I, is our coordinate for our midpoint, and then half of what the function is at that midpoint. So halfway up there. Okay. Now, if we think about it here, we're going to take that point, okay, and we want to think about the distance that we are to the x-axis and to the y-axis here, right? So if we're thinking about this in terms of moments and all of that, the area of each rectangle here is going to be f of, it's going to be the function at the midpoint, and we're going to multiply it by delta x. Delta x is going to be the width of that rectangle there. The mass is going to be the density times the area. So we're just going to multiply that by the density, which is the row there, times what we had for the area. The moment about the y-axis is going to be the mass times the distance to the y-axis. The distance to the y-axis is just going to be our x bar sub I. Okay? So this moment is going to be the density times what the function's equal to at that point, times delta x, times, again, this is the distance to the y-axis right there. For the entire plate here, the moment is the sum of all the moments. And then we're going to take the limit as the number of rectangles is infinitely large. So the total for this here is going to be the limit as n approaches infinity. N, again, is the number of rectangles. We're going to add up from 1 to n everything that we have here. Okay? Now, we've done this many times in calculus before. We recognize that this is just an integral here. If we add up the number of rectangles, if we're summing this all up, pull the density outside, this will be the integral from a to b of x times f of x dx. Okay. F of x is coming from this. Your x is coming from this right here. And then the delta x is going to be your dx there. Now, the x location of the centroid is going to be your moment divided by the total mass, okay, which is going to be the moment that we just figured out up there. And then the total mass is going to be the density times the total area. Now, if you notice here, we're going to have a density in both the numerator and the denominator. And then the total area is just our normal integral from a to b of f of x dx. So that's going to simplify down to 1 over the area just by normal integral calculations. And then we're going to go integral from a to b of x times f of x dx. Okay, again, this is getting us the x coordinate of the centroid. Okay, now if we do the same thing with the moment about the x-axis, it's going to be the mass times the distance to the x-axis, which is going to be our 1/2 f of x bar that we have here. So this is going to be density. Our function is equal to here times delta x times 1/2 f of x bar for the ith interval. Okay, so again, same kind of thing to get the sum. We're going to do the limit as n goes to infinity. We're going to sum this up from 1 to n. All of this good stuff that we have right here. And what you get out of this is the density times the integral of 1/2 f of x squared dx. Similarly, we got y bar is going to be the moment divided by the total mass. It's going to be that same moment divided by, so we got our integral that we have here, 1/2 f of x squared dx. We're going to divide it by density times just the normal integral. Okay, and then that is going to spit out for us a y bar that is 1 over the area, and then we're going to go 1/2 f of x squared dx. Okay, and so this is how we are going to find the centroid if we have a uniform density. Okay, so that density ends up getting canceled out because we have it in 2 locations. We have it on the top and the bottom of our fraction there. Now, if we had another function on the bottom that was defined in the bottom region, the bottom of the region, then we would have to alter this a little bit, right? Because instead of having f of x as that whole distance, now we're looking at f of x minus g of x. But if we just have this situation here, this is how we're coming up.